Hello students, good morning to all. Welcome to your beautiful channel Firjan. See, today we discuss electrostatic potential and capacitance. It is the second lesson in 12th standard. See, this is the first video in this one. See, last before we discuss electric charges and electric fields. Totally 15 videos, 15 hours is there. It is very good content who and all attempting the JEE and NEET. So please see that videos and subscribe my channel. So now we discuss electrostatic potential and capacitance. In this one, first video, introduction video this one. So first we discuss electric potential. See, before this electric potential, we discuss first electric potential difference. Electric potential difference. See, electric potential difference. So, how to represent now this one electric potential difference? By using delta V, we can represent. So, delta V means change in potential. So, that we call it as electric potential difference. For defining this, we want 2 points. For example, see, this is 1 point, it is a 2 point. See here. Here we can take test charge. Test charge na Q naught is the test charge. This is test charge. It is the test charge. So what is the use now this one? It is always positive. It has no electric field. It is very small. So test charge is very small, always positive. It is it has no electric field. So that is the test charge. Why we are taking this test charge now? We want to define electric potential difference between these 2 points. So means charge is moving between these 2 points. So means in moving charge, between 2 points, see here in moving charge between here to here. So definitely we want to do some work. Without work it will not moving. See how much of work is done on test charge in bringing or taking from B point to A point. That work done on charge we call it as electric potential difference. While moving charge from B point to A point, one condition is there. The charge should be moved very slowly. Charge should be moved very slowly. Why it will move very slowly now? There is no change in kinetic energy. There is no change in kinetic energy and no change in speed. No change in speed of Q naught. So then only the definition is correct. Electric potential means amount of work done act on test charge Q naught in bringing B point to A point. That amount of work done on test to charge against electric field, we call it as electric potential difference. Electric potential difference. This is the initial point, it is the final point. While moving charge, these two are the condition. Definitely charge is moving in between 2 points. Charge should be moved very slowly. It will move speed now, it will move with some speed. What happened? A change in kinetic energy is there. So definition is not correct. So that's why charge should be moved very slowly from B point to A point. For that, we have to do some work. That work on charge, we call it as electric potential difference. So that here potential is at B point is VB, potential on A point is VA. So what is the potential difference now? It is initial point, it is final point. See final minus VA minus VB equal to work done by external agent from A to B to A. Work done by external agent from where to where? B to A. Charge is moving from B to A. It is final, it is initial. Final minus initial. Final potential minus initial potential. we call it as potential difference or change in potential. This work done by external agent B to A on test charge, we call it as electric potential difference. Electric potential difference, this is the electric potential. This means amount of work done on test charge, we call it as electric potential difference. Then only it will move from B point to A point. So while moving charge, this is the condition, charge should be moved very slowly, there is no change in kinetic energy, no change in speed of q naught test charge. Yes, now see, this is the electric potential difference. For example, electric potential at a point means here, so electric potential at a point defining V infinity tends to 0. See, for example, here this point we can define electric potential. For defining electric potential at point A, definitely we can select one more point, that definitely infinity, at infinity. Here test charge is there, q naught. Q naught is the test charge, or we can take unit positive charge. So q naught is the test charge at infinity. It is moving from infinity to A point. We have to do some work, external work against electric field or electric force. That amount of work done on test charge in bringing infinity to A point. How much is work done on test charge? That work done on test charge from infinity to A point, we call it as electric potential at a point A. How to write now here this one? It is the initial, it is the final. See, final minus initial. See, that equal to work done by external agent. Where to where? Infinity to A point on test charge. See, what potential at infinity is 0, so that why we can write here 0. So means potential at a point A equal to work done by external agent, where to where? Infinity to A point on test charge. This is called as electric potential at a particular point. Means at particular point means A here. At particular point is what here? A. Potential at a point. Electric potential at a point is defined as work done in bringing unit positive charge or test charge from infinity to required point against electric force or electric field, we call it as electric potential at a point. Electric potential at a point. So whenever we define electric potential, definitely this condition is must and should. Charge should be moved very slowly, there is no change in kinetic energy, no change in speed of test charge or unit positive charge. It is the definition of electric potential difference or electric potential. For this one, we have some note points is there. What is the here now? Important notes. First one, work done by external agent should be considered. Work done by external agent should be considered. Means this work is against electric force, against electric force. This is the first condition. See, work done by external agent should be considered, this work is against electric force, work is against electric force. Second one is, so second point here, this work is, whatever the work done by external agent, this work is path independent. Path independent. Why we are saying path independent now? See, electric force, because electric force is conservative force. Conservative force. Electric force is conservative. Conservative means, force means that force is not depend upon, work done by conservative force is not depend on path, it's depend on only initial and final position. For example, see, work done from A point to B point, we can select different paths. This is the one path, this is the second path, this is the other path. See, third path. See, work done by first path, which is equal to work done by second path, which is equal to work done by third path. Means only depends upon initial position and final position. Such forces we call it as conservative force. Work done by such force we call it as conservative force. See, What are that forces now? Electric force and gravitational force are conservative forces. Electric force and gravitational force are conservative forces. In work done by conservative force in a closed path A to B, B to A is always zero. Means work done by conservative force in a closed path is zero. That's why work done by conservative force in a closed path we can say zero. So it is not depends upon path, only depends upon initial and final position. See what is the third condition now? So test charge should be very small. Test charge is very small, no electric field around it, electric field around it. When it not produces any electric field. These are the conditions while defining electric potential difference or electric potential at a point. What is the first condition? Work done by external agent should be considered. This work is against electric force. Always it work is against electric force. See, it is the electric force working this direction. Work done by external agent is working this direction. See, this work is path independent. It does not depends upon path. Whatever the path, because if electric force is conservative, because electric force is conservative, it is not depends on path, it depends upon only initial and final position, where to where moving, that what is initial position, what is final position, depends on that only. So that's why here see A to B we have different paths. There is first path, second path, third path. Work done by first path equal to work done by second path, work done by third path. Not depends upon path, only depends upon initial and final position. That's why it is conservative force. Conservative forces are always depends on initial and final position, not depends on path. See, conservative means work done by conservative force in a closed path is zero. Work done by conservative force in a closed path is zero. That's why we can write work done from A to B equal to work done minus of work done B to A. Minus of work done by B to A. Work done by conservative force B to A. So this is the conditions for while defining electric potential and electric potential differences. Now electric potential difference means amount of work done on test charge in bringing B point to A point against electric force or electric field. We call it as electric potential difference. Electric potential difference. Electric potential at a point means amount of work done in bringing test charge from infinity to required point against electric field or electric field force is called as electric potential at a particular point. At a particular point. This is the basic information about electric potential difference and electric potential at a point. Electric potential and electric potential difference at a point. See, next we discuss how to define electric potential due to a point charge. What is the electric potential due to point charge? See, electric potential right here, electric potential due to point charge, that is q. We can take q is the point charge. Here we can define, see, this is the point charge q or distance from the charge at point P. What is the potential? That we can define. For that, what we can do now, here we can select one infinite point, infinity. So here test charge is there. Here see test charge. See, test charge is moving from here to infinity to required point. We have to do some work, external work done on test charge in bringing from infinity to a point. We can write it is initial position, it is final position. So that one I write here, work done by external agent, where to where, infinity to a point on test charge. See, that we call it as electric potential at a point P. It is initial, it is final. So means final minus initial, Vp minus V infinity, that equal to what now here? Potential. So means at P is Vp, potential at infinity is V infinity, Vp minus V infinity. Why? By it is the initial point, it is the final point. See, amount of work done in bringing test charge from infinity to P point. That amount of work done on test charge we call it as potential difference. That potential difference is Vp minus V infinity, that equal to work done by external agent, where to vary charge moving infinity to A on test charge. This is called as electric potential at point P. We derive this one. For that, what we can do now, first here we will calculate work done by external agent. P to infinity we can calculate, but we are defining infinity to P, but we calculate P to infinity. See, work done by external agent infinity to P, we can write it as minus of work done by external agent P to infinity. Before we discussed work done by conservative force in a closed path is 0. See, A to B or B to A. What now here work done by external agent A to B, B to B, B to A equal to work done by A to B equal to minus of work done by B to A we can write. So like this here also, see, infinity to P, P to infinity, closed path, work done by conservative force is 0. That's why infinity to P equal to what we can write, minus of external agent P to infinity we can take. So we can calculate this and we can substitute, we get the value. See, work done by external agent infinity to P, we can write it as minus of work done by external agent P to infinity. For that, here see, this is the test charge, sorry, charge, point charge at point P, here or distance. See here, what now here infinity we can moving. See here, electric force is this direction acting, Fe, electric force is acting rightwards. So because of this electric force, here test charge is there, it is moving from P to infinity, so it speed is changes. So speed change means electric but not defined electric potential. So what we can do here, opposite here, external force we are acting, due to this external force, external work done. So here electric force is this direction, force, external force is this direction. See, both are displacement, this direction d or displacement. See what now here work done by external agent equal to what now here, force is, electric force is this direction, work done by external force is this direction. So external force this direction, so which is exactly not equal but approximately equal to electric force. That way we can write what is the electric force at point P due to point charge now, K Q Q naught by R square. It is the electric force on test charge due to point charge. See, all distance from this, what, K Q Q naught by R square. See, for displacing d or distance, what now here electric force is acting this direction. So electric force is acting means the speed is changes. So according to definition of electric potential, there is no change in speed, no change in kinetic energy. For that we are applying a external force. So when external force is acting on Q naught, its speed is not changed. It will move with constant speed and takes infinite steps and reaches to infinity. So that's why we can take here work done by external force we are acting against electric force. Force is this direction, displacement this direction. What now here? Force F external into displacement. We can write F external dr cos 180 we can write. Cos 180. Why? Because here see, here means displacement in this direction, external force this direction. So what is the angle here? 180. So F dot dr means F dr cos 180. What is the external force here? Equal to electric force. So that's why we can write here, see, work done by external agent, where it moving, P to infinity. So to P to infinity, what we can write, cos 180 minus F external into dr. See here, from here to here dr, this dr up to reaching infinity, it takes infinite steps. That all infinite steps we can add now, we take integration. So we can take integration, where to where, P point to infinity. We can write here P to infinity, P to infinity, F external dot F external dr. F external means which is approximately equal to electric force. What is the electric force at P point due to point charge? K Q naught by R square. I write here. See, that equal to integral minus K Q q naught by r square dr. See, work done by external agent p to infinity, p to infinity is minus of integral k q naught by r square dr. What is the p value here? R, infinity. So r to infinity we can write here, r to infinity. Now see here, work done by external agent, where to where? P to infinity, p to infinity. See here, minus of k q naught constant we can write outside, integral r to infinity. So what? 1 by r square dr, integral 1 by r square equal to dr equal to minus 1 by r. Why now here? See, integral r power minus 2 we can write r square, 1 by r square. So that means dr here, what now formula? X power n dx equal to x power n plus 1 by n plus 1. Here r power minus 2 plus 1 by minus 2 plus 1. So means minus 2 plus 1 means r power minus 1 by minus 1. So means minus 1 by r. What we get? Minus 1 by r. So this one, so integral of 1 by r square dr equal to what we can write? Minus 1 by r, minus 1 by r. Here I write, see, minus of k q naught into minus 1 by r. What is the interval now here? R to infinity, r to infinity. Work done by external agent p to infinity equal to what we can write now here? See, I write here, work done by external agent p to infinity equal to, first we can write upper limit. So means minus k q naught, so minus 1 by infinity. Later, so minus of minus plus, so means plus 1 by r. Why we can write plus now here? Upper limit minus lower limit. Lower limit minus, already minus is there, minus of minus plus, so 1 by r. See here, 1 by infinity 0. So that's why here we can write work done by external agent p to infinity equal to minus k q naught by r we get. So this is the work done by external agent. Where to where moving? P to infinity moving. For moving p to infinity, what is the work done now here? Minus of k q naught by r. But we want what? What is the actual definition? Vp minus v infinity equal to work done by external agent infinity to a we want. So infinity to a means, or infinity to p, sorry, infinity to p. Infinity to p means here minus of external agent p to infinity. I write here, work done by external agent p to, sorry, infinity to p equal to what we can write? Minus of work done by external agent p to infinity. So minus already is there, minus of k q naught by r. This minus minus cancel. What we get here? Work done by external agent infinity to p equal to k q naught by r. So this is the work done by external agent infinity to p point. What is the work done we can get now? Work done by external agent, see here, p to infinity, sorry, infinity to p is k q naught by r. We get, this is the value we are getting after this all process. So what is the work done by external agent? Where to where moving? Infinity to p point. What? K q naught by r. See, what is the formula actually? Vp minus v infinity equal to work done by external agent infinity to p on test charge. See, I write here, Vp minus v infinity. So work done by external agent, what we are getting from infinity to p? K q naught by r by q naught. See, q naught cancel. What we get now here? Vp minus v infinity, that equal to kq by r. See, v infinity is 0. What we get now? Finally, potential at point p equal to kq by r. This is the definition of electric potential at point p or distance from point charge. Yes, now see once again, first what we can do now here? This is the point charge, this point, what is the potential we can derive? For that, what we can do? We can select another infinite, another point, that is infinity. Here to here test charge is moving. For that moving test charge from here to infinity to p, we have to do some work, that is External work done by external agent in bringing test charge from infinity to P point, infinity to P point. We have to do that work done on test charge. We call it as electric potential difference we call. So that is, it is initial, it is final. So final minus initial, Vp minus V infinity equal to work done by external agent where to where, infinity to P on test charge. But we will calculate work done by external agent P to infinity, we calculate that we can utilize later. See, work done by external agent infinity to P means minus of work done by external agent P to infinity. See here, this is the test charge, sorry, point charge, here point, here we find out. For that, in this test charge, some electric force is acting, that is Fe. What is that now? K Q Q naught by R square. Due to this electric force, test charge is moving with some speed. But according to definition, there is no change in speed, no change in kinetic energy. That's why we are doing some external force acting on this one, do some work. So displacement is dr, work is here this direction, displacement is this direction, both are in opposite. What is the angle now here? 180. So work done by external agent where to where, P to infinity, work force into displacement. So dot product now F external into dr cos 180, cos 180 minus we can write. So integral, why we are taking integral now? This one dr, this one dr, this one dr, dr, dr. How many is there? Infinite steps is there. This infinite steps we can add means work done by external agent P to infinity minus of P to infinity. Here see where to where moving, here to here, P to infinity. P means or distance, or to infinity. What is the external force? K Q Q naught by R square. Actually there is electric force which is equal to external force. That's why we can write here K Q Q naught by R square dr. See, R to infinity, K Q Q naught constant we can write out 1 by R square. 1 by R square means minus 1 by R. So upper limit, later lower limit. Here we can substitute upper limit 1 by infinity plus 1 by R. 1 by infinity is 0. So work done by external agent P to infinity equal to minus of K Q Q naught by R. See, work done by external agent infinity to P we want. Actually P to infinity we find out, we want infinity to P. Infinity to P means what? See, work done by external agent infinity to P equal to minus of work done by external agent P to infinity. Why? Because work done by conservative force in a closed path is 0. That's why P to infinity, which is equal to minus of work done by infinity to P, or infinity to P equal to minus of P to infinity. We can write this one. This one we know. So minus of minus plus. So what we get? K Q Q naught by R. Actually definition is what here? Vp minus V infinity equal to work done by external agent infinity to P. What is the work done by external agent? Infinity to P, K Q Q naught by R. That I write here K Q Q naught by R by Q naught. Q naught cancel, K Q by R. Vp minus V infinity. V infinity is 0. Vp equal to K Q by R. This is the derivation of electric potential at a point P or distance from the point charge Q. Point charge Q. So what is the formula for this now? Vp equal to K Q by R. This is the electric potential at a particular point or distance from the point charge. Okay now? See, by using this we can solve the problems. See, what now? First problem, this is the electric potential due to point charge. What is the formula? Kq by r distance na, Kq by r. See, first we solve first one, first problem. What now here? See, two charges. What now here? Q and minus 3q. Two charges which are placed at r distance between them. What is the place distance between them now? R. Where what is, where is potential 0, where is potential 0 between, with potential 0, line joining, line joining between them at all distance. What now here? See, where is V0? Line joining two charges, line joining two charges, line joining charges between them at all distance. In this case, where potential is 0, in between the charges, outside the charges, both we find out. See, for example, here this point at y point potentially 0 we consider. So means due to this first charge some potential here, due to second charge some potential here, there is some is 0 at a particular point, that particular point in between them and outside both we can find out. See here, what is the potential at p point due to point charge or distance k q by r. Here we can use with sign, with sign, plus charge na plus we can write, minus charge na minus we can write. See here, where is v0 line joining between them at all distance. Yes, now see here, potential at y we write. So what here, due to first charge v1, due to second charge v2. See here, Vy, first we can find out potential at due to 1. See, potential due to this one. This is total distance is r. This distance we don't know. We consider x. This distance automatically r minus x. See here, due to this charge, what is the potential at y now? So V1 equal to charge is q, kq by distance is x. This is the charge. What now, plus charge? So we can take plus. Potential due to second charge on at y. See what here, minus k 3q by r minus x. This is the potential at y due to second charge. See total na vy equal to v1 kq by x minus 3kq by r minus x, or minus x. But we consider here potential at y equal to 0. So we can take here 0. So 0 equal to what? Kq by x minus 3kq by r minus x. It will changes to this side. What we get now here, see, 3kq by r minus x equal to kq by x here. Q cancel, kk cancel. What we get here, 3 by r minus x equal to 1 by x. Cross multiplication now here, see, 3x equal to r minus x. X changes to this side, 3x plus x equal to r. So 4x equal to r. So x equal to r by 4. Means from first charge, how much distance na? Potentially 0, r by 4 distance is potentially 0. Means potential is Vy equal to 0 at r by 4 distance from smaller charge. Smaller charge. For example, this one outside where it is potential 0. For example, see, this is charge 1, it is charge 2. In between them distance is all distance, but outside where some particular point we can take potentially 0. This point potentially 0. So due to first charge here potential, this distance is x we can take. Due to this charge potential here, both sum we get 0. So that we find out. See, Vy equal to V1 plus V2. So V1 due to first charge potential, this is the first charge potential here, x distance is x. So we can write kq by x. Due to second charge, due to this one, so potential, what is the potential at y point? So distance is here r plus x. We can write here minus k into 3q by, what is the distance here, r plus x. We can write here r plus x. Total now here potential at y equal to this one and this one. So kq by x minus 3kq by r plus x. See, potential at y, here we can take potential at y equal to 0 we consider. So means here see, v y equal to 0, what we can write, kq by x minus 3kq by r plus x. It will changes to here, plus we get 3kq by r plus x equal to kq by x. See, k cancel, q cancel. What we get here, 3 by r plus x equal to 1 by x. Cross multiplication, 3x equal to r plus x. X changes to this side, 3x minus x equal to r, 2x equal to r, x equal to r by 2. Where potential is 0 outside from some smaller charge now, r by 2 distance from smaller charge from smaller charge outside point r by 2 distance potentially 0. Where is potentially 0? Line joining between them at r distance now. So in between na r by 4 distance from smaller charge, outside na r by 2 distance from the smaller charge. So that is potential is 0. Outside is r by 2 distance, in between them is r by 4 distance. This is the solution. See next one, second one. So potential due to uniformly charged ring, due to uniformly charged ring, what is the potential at x distance from the center along the axis? That we can derive an equation. See potential due to uniformly charged ring. See I write here potential potential due to uniformly charged ring, uniformly charged ring x distance from center along axis, that we derive now. See here electric potential due to uniformly charged ring x distance from center along axis of ring, axis of ring. For example, see this is the ring, this is the center, this distance is or why not radius, this one from center or distance along the axis x distance at point P, this point, what is the potential that we want to find out? It is extended object. So for extended object, it is not valid. So we can take point charges. So this electric potential is valid for point charges only. We know point charges. What is the potential at a point charge due to point charge at all distance from the point charge now? See potential at P equal to k q by r or distance. So with sign we know this one. So this is the formula for with sign. So plus means plus, minus means minus. So means electric potential at point P or distance from the point charge, what is the na Vp equal to kq by r, kq by r. But due to this uniformly charged ring, what is the potential at point P, x distance from the center of the uniformly charged ring along the axis? So for that it is extended object. That's why what we can do now, this one now we can divide into small charges, small elementary parts, dq. We can cut dq part, and this due to this dq, what is the potential at point P? We find out. For that, see here. So this distance is or radius. It is x. What is this distance now? R equal to, it is right angle triangle. So means root of r square plus x square. This is the distance between dq and P point. See dq, very small charge. So due to small charge, elemental part, what is the potential? dV only. So we can write here dV equal to, what is the formula? kq by r. K q now here dq, k dq by r means here this is root of x square plus r square. I write here root of x square plus r square. Due to this dq, what is the potential at point P along the axis x distance from the center na k dq by root of x square plus r square. See here, due to this dq, we can take here one more dq. Due to this dq, what is the potential at this point? Same. So dV equal to k dq. I write here dV equal to k dq by root of x square plus r square. Why? Because see, it is the ring, it is the axis. From here how much distance is there? Here also same distance, here also same distance, this side all sides same distance, r is same. Here also r equal to what? Root of x square plus r square only. Why? Because from here to here, here to here, here we can cut now here dq. From here to here, here we can cut now dq. From here to here, so means same distance, small r same, x same, r same. What changes here? Only dq. See this type of dv's, how many is there? This total ring infinite is there. Wherever infinite we can add now, we can take integration. So that is integral dv equal to integral of k dq by root of x square plus r square. It is the total potential due to uniformly charged ring at point P. What is integral dv? Integral dv means v at point P equal to integral k is constant, root of x square plus r square is constant. What we can write here? Integral dq only changes, remaining will be constant, k constant, x constant, capital R also constant. That's why integral dq means potential at P equal to k by root of x square plus r square, root of x square plus r square. Integral dq means q we can write. Yes na? See, potential at point P, x distance from the center of the uniformly charged ring is k q by root of x square plus r square. For example, here you can take total charge capital Q you can take na. Here we can write capital Q also, small q, whatever we can take, that is not a issue. So what potential at point P due to uniformly charged ring, x distance from the center is k q by root of x square plus r square. For example, this total charge we can take capital Q now. Here we can write capital Q only. Here we can write capital Q. Here also we can write capital Q. K q by root of x square plus r square. It is the potential due to uniformly charged ring, x distance from the center of uniformly charged ring along the axis. What is the potential? K q by root of x square plus r square. See here, this x is 0. For example, x is 0 means at center. If x equal to 0, if x equal to 0 means what is the potential? Means at center only. Potential at center equal to what now here? K q by x is 0 means 0 square 0, r only, r square is there. So r square means square root cancel. What we can get now? Potential at center equal to k q by r. See here, what is the potential at center of the uniformly charged ring na? K q by capital R. C means it will be act like point charge. See, point charge formula is what? Potential at point charge at all distance from the point charge na, Vp equal to kq by r. Here same like this is there, kq by r means it seems as if whole charge will be kept at center of the ring. So that case, at this point, what is the potential now here? Vc equal to kq by capital R. Vc equal to what? Kq by capital R. This is the derivation of electric potential due to uniformly charged ring, x distance from the center along the axis. Again listen, this is the uniformly charged ring. Charge is distributed uniformly. What charge now? Plus q charge. X distance from the center, this is the center, it is the radius, x distance from center at point P, we find out what is the electric potential. For that, what we can do now? It is extended charge, that's why we can cut into small elemental parts, that is dq. Due to this dq, what is the potential? dv equal to k dq by root of x square plus r square. Why we are writing root of x square plus r square now? This distance is x, this distance r, this distance we want, this is right angle. So r equal to what? Root of r square plus x square. That's why we can write here root of x square plus r square. See, dv, this dq, this value, this dq, same, this dq. Why? Because now it is the ring, it is the axis. From here same distance, here same distance, here same distance, means same distance. That's why dv's, all dv's are same value. So dv's, all dv's added, we get the total potential due to uniformly charged ring at point P, x distance from this. So that we can take added now integration, small parts added means infinite parts. We can take integration, integral dv, integral k dq by root of x square plus r square. K and d root of x square plus r square is constant. We write integral dq. Integral dq means q. What is the charge here? Capital Q. That's why we can write capital Q. Kq by root of x square plus r square. It is the potential at point P, x distance from that center, uniformly charged ring. So if x equal to 0, this x is 0 means at center, what is the potential now? Vc equal to kq by r. Kq by r. This is the potential due to uniformly charged ring at point P, x distance from the center along the axis. Along the axis. This is the formula for center, kq by capital R. Yes, na? This is the derivation of electric potential due to uniformly charged ring. Now we discuss one problem this on according to this. See, we can solve. What is the problem now? Amount of work done in moving. I write problem here. See, amount of work done. Amount of work done in moving charge q from center of second ring to first center of first ring, center of first ring, that we want to find out. First ring, what is the amount of work done, so that we want to find out. See here, this is the first ring. See, it is the first ring, it is the center c1. See, its radius is capital R. See, charge is plus q. See, one more ring is there here. See, this is the second ring, its center is c2, its radius is capital R here also, charge is minus q. See, what is the distance between these two rings now? Capital R distance. Here, test it, here charge is there q, here q charge is there. This q charge is moving from center of second ring to center of first ring. What is the work done we can do? What is what amount of work is done on this charge q, then in moving from c2 to c1, that we want to find out. First we find out what is the potential at first ring, we find out what is the potential at second ring, we find out. For that, see, potential at first ring we have. See, we want to find out first potential at first ring means, due to ring at center we have one potential. See, potential due to uniformly charged ring means at x distance. Now what is the formula? K q by root of x square plus r square. It is the formula for electric potential due to uniformly charged ring x distance from center along the axis. At center, now what is the formula? K q by capital R. These are the formulas for uniformly charged ring. It is x distance formula, it is center formula. See, we can use that one here. See, potential at V, potential at first ring. What now here two cases is there. One, due to itself potential is there, due to second ring potential is there. Due to second ring, what the distance now here? See, small r distance. Due to this ring, it is r distance, means here what is the formula? This is one, this one square, so means r square plus r square, means what is the distance now here? R equal to root 2r distance. Small r is for this ring. What is the distance now here? This point, r distance, root 2r. So for that, due to this one potential, due to this one r distance, here one potential. So that rate one potential on one due to first ring, potential on one means due to second ring, due to second ring or distance from the second ring along the axis. So that's why we can write here center point this one. So means what we can write? K q by capital R. So this is x distance, means r distance from this ring, here potential. So that is charge is minus q here, minus k q by distance is r. R means what here? Root 2r. This is the potential at first ring. This is the potential at first ring. We want to find out potential at second ring. So this also same, two cases there. Itself one potential, due to this one is one potential. So means potential at 2 due to second ring, due to second ring. See, potential at second point, second point. So means due to first ring. So we can write due to second ring, it is center point. Due to first ring, see here, for this it is the x distance. So means what is the radius here? Same, r square plus r square root of. So what we get? Root 2r. So I write here V2 potential at 2 second ring, center of second ring equal to k. So second ring itself is center. So what you here can write? Minus k q by r. This will be act as x distance, means what we can write formula this one. So means k q by root 2 r, root 2 r. It is the potential at first ring, it is the potential at second ring. So V1, this is V1, V2. So where to where moving charge? Here to here. What is the potential difference we can write? It is initial, it is final. So V1 minus V2 equal to work done by external agent, where to where moving, second point to first point. So means second to first one on charge. It is the potential difference formula. See here potential is V1, it is the potential. Here potential is V2. Where to where charge is moving? Center of second ring to center of first ring. So we can write V1 minus V2 equal to work done by external agent in bringing second ring, center of second ring to center of first ring on test charge. It's on charge. It is. So what we want, work done by external agent we want. So that's why we can write this one. It will changes to here. See work done by external agent equal to V1 minus V2 into Q we can write. V1 means this is the value. V2 means this is the value. We can substitute there. Work done by external agent. What is the amount of work done? So that is where to where moving, second point to first point. Yes, now see here V1 KQ by R minus KQ by root 2R. KQ by root 2R minus of here it's one already minus is there. So minus KQ by R plus KQ by root 2R. It is 1. See minus into minus plus. So I write here KQ by R minus KQ by root 2R. See here minus into minus plus KQ by R minus into plus minus KQ by root 2R. See here this KQ by R, this KQ by R. What we can write? 2KQ by R is this one. So minus 2KQ by root 2R. Here KQ by R common now. See we can write KQ by R common means what we get into Q also is there. Totally into this Q is there. Here we can write Q. See here in Q. See what we get now here KQ by R. 2 minus 2 by root 2 into Q. Yes na? See I write here last point. See work done by external agent 2 to 1. What we can get now KQ by R. Here 2 means this Q we can write here Q. So what we get to 2 minus this 2 can be written as root 2 into root 2. 1 root 2 cancel. What we get now? This is the answer. See what is the amount of work done in moving charge center of second ring to center of first ring now? K capital Q small q by R into 2 minus root 2. This is the amount of work done in moving charge from center of second ring to center of first ring. What is K capital Q small q by R into 2 minus root 2. This is the amount of work done. Amount of work done. Okay, na? Next one we discuss electric potential due to uniformly charged linear rod. So that we want to find out. So what now this one? Electric potential due to uniformly charged linear rod. See electric potential due to uniformly charged linear rod of length capital L. L distance from the rod. L distance from rod. This is the problem. See once electric potential due to uniformly charged linear rod of length L. L distance from the rod at point P. At point P, we want to find out what is the electric potential. See for example here, this is the uniformly charged linear rod. This is the uniformly charged linear rod. In this one, charge is plus is there, positive charge is there. This length is, this length is capital L. This length is capital L. From here at point P, what is the distance now? This distance is L. This distance also L. What is the potential at point P? That we find out. It is extended object. Extended object we can't define. We can define only for potential. Electric potential is defined for point charges. So for that, what we can do now here, we can cut small part. This part charge is dq, length is dx. From here, what is the distance now? This one, x distance. See, what is the electric potential due to dq? dv is there. So what that dv? So dv equal to k dq by distance is what here? X distance. This is the potential due to dq at point P, x distance. dv equal to k dq by x. This type of here, from this point we can take, what is this charge now here? dq, distance length is dx. So what we get? dv, what now? K dq by x distance only. Here we can take what now? This one. So dq, what we get now here? dv equal to k dq by x we can get. This all, how many is there here? Infinity is there. This all we can add, we get the total potential at point P due to uniformly charged linear rod. See, for that we can take add means integration. Integral dv equal to integral k dq by x. Here see, rod length starts at L, ends at 2L, L plus L, 2L. Starts L, for starting point is at L distance, ending point is L plus L, 2L distance. That's why we can take interval L to 2L we can take, L to 2L we can take. See now, integral dv means V, means potential at P equal to, see here, k dq by dx. dq is variable, x also variable. X now here see, it is x distance, x1, x2, x3 changes, value changes, means variable. So two variables now can't integrate. So that's why what we can take now here, linear charge density we can use. Linear charge density. What is linear charge density? Means charge per unit length. Charge per unit length. Now see here, linear charge density. I write here linear charge density. Linear charge density lambda equal to charge per unit length. Charge per unit length. See here, charge now here capital Q, unit length is L, we can write Q by L. See here, lambda equal to Q by L. Yes na, Q by L, Q by L. This is the formula for linear charge density, charge per unit length. For example, here see, what is the charge here? dq, length is dx. What is the lambda here? Lambda equal to dq by dx. From that, dq equal to what we can write? dq equal to lambda dx. This we can use here. See, instead of dq we can write lambda dx. I write here integral L to 2L. Instead of dq we can write lambda dx by x. Now see, one variable is there, with respect to dx only is we can do. See here, so k lambda constant we write outside, so that is k lambda where to where? L to 2L, 1 by x dx. 1 by x dx means log x, k lambda log x where to where? L to 2L interval, L to 2L interval. See, I write here potential at P equal to first upper limit, later lower limit. So means k lambda upper limit log 2L minus log L. So yes na, so log A minus log B means what here? Log A minus log B equal to log A by B. This formula we can use here. See, potential at P equal to k lambda log of 2L by L. So L cancel. What we get now here? K lambda log 2 we get. This is the potential at point P. L distance from the linear charged rod. Linearly, uniformly charged linear rod. What is that one? K lambda log 2. Lambda means q by L. We can write here potential at P equal to k q by L log 2. So k means what now, 1 by 4 pi epsilon naught. We can write instead of this one. So potential at P equal to q by 4 pi epsilon naught L log 2. This is the potential at point P, L distance from the uniformly charged linear rod. That is the potential. See again once, it is the uniformly charged linear rod. It has a charge capital Q. Capital Q charge is there. It will be distributed uniformly. L distance from that rod at P point, we want to find out what is the electric potential. For that, what we can take now here, this is extended charge, so it is not valid for the defining electric potential. So we can cut into elementary parts. Dq length is dx. Due to this dq, x distance from the point P, what is the potential now? Dv equal to k dq by x. So this charge dq, this dq charge k dq by dx, k dq by x. This term k dq by x means this type of how many is there here? Infinite is there. So that's why we can add infinite. We can use integration. So that's why I write integral dv equal to where to where? L distance starting point, ending point L plus L to L distance. That's why L to L k dq by x. Here x variable, here dq, different is there. So we can take into one. So different variables is there, we can convert into one variable now. For that we can use linear charge density. What is the linear charge density? Lambda equal to charge per unit length. Charge is q, length is L. Lambda equal to q by L. But here we have charge dq, length is dx. So lambda equal to what? Dq by dx. Dq equal to lambda into dx. Lambda into dx. Instead of dq, we can write lambda dx by x. K lambda outside. Why? Because constant. Integral L to 2L 1 by x dx. 1 by x dx na log x. Where to where? L to 2L. So k lambda log of upper limit interval 2L, lower interval L. See, log A minus log B means log A by B. We can write 2L by L. L cancel. So means potential at P equal to k lambda log 2. Here lambda means q by L. I write here q by L. K q by L log 2. So Vp potential at P equal to k means what? K equal to 1 by 4 pi epsilon naught. I write here q by 4 pi epsilon naught L log 2. This is the potential due to uniformly charged linear rod, L distance from the rod at point P. What is the that value now? Vp equal to q by 4 pi epsilon naught capital L log 2. This is the potential. See, now we can do the problem on this base. See next one now problem. What is the problem now here? Two charges. 1 minute. See, two charges. Two charges. One is 5 into 10 power minus 8 coulombs, and other one is minus 3 into 10 power minus 8 coulombs, located at 16 centimeters apart. 16 centimeters apart. Apart. At what point? At what point electric potential, electric potential, electric potential is zero? That we can find out. At what point, at what distance electric potential is zero? In line joining two charges, line joining two charges. It's not that we want to find out. See here, what is the first charge? 5 into 10 power minus 8 coulombs. Second charge, minus 3 into 10 power minus 8 coulombs. This distance between them is 16 centimeters. Yes, na? For example, here, at what point we don't know. So, but we can select at y point, potentially 0. So, y potential at y equal to, this is the first charge, this is the second charge. Due to first charge, V1, due to second charge, V2. We can add, we get the value. So, why? Because potential at y equal to 0. Potential at Why not? Due to this one, we don't know distance. We can take here x. This distance automatically 16 minus x. Why? Because total distance is 16. So we can write here, this is 0, that equal to v1. So means k into 5 into 10 power minus 8 by x distance. Minus here, why? Because minus charge is there. K 3 into 10 power 8 minus 8 by 16 minus x. It will change us to this side. See what we can get now here, minus k in, sorry, plus k into 3 into 10 power 8 minus 8 by 16 minus x equal to this one. So k into 5 into 10 power minus 8 coulombs. Here see, this value cancel, k cancel, by x here is there. X now, see what we get, 16 by, sorry, 3 by 16 minus x, this equal to 5 by x. Cross multiplication. See what we get now here, 3x equal to 16 5 jar 80, 5 into x minus 5x. See it will change us to here, means 3x plus 5x equal to 80. 8x equal to 80. So 8 ones, 8 tens, means x equal to 10. So means 10 centimeters from charge 5 into 10 power minus 8, electric potential is 0. This is the solution. See, this is one charge, this is another charge. At what point? Means at particular point we can take y, that is 0. So due to this potential V1, due to this potential V2, we can write, it will change us to here. We can simplify, what is the distance now? At x equal to 10 centimeter, from where? 5 into 10 power minus 8 coulomb. From this side, 10 centimeter distance, potential is 0. This is the introduction of electrostatic potential and capacitance. Please see my videos, subscribe the channel and share to your friends. It is very important and useful information who and all attempting the JEE and NEET. So definitely it is very useful. Please see my videos and subscribe my channel. Thank you.